Okay, so welcome to our third and this series of reaction videos, and you've probably gone through addition and elimination, and now we're going to start talking about substitution reactions. Substitution reactions, as the names say, imply some sort of replacement. So something on our organic molecule here is going to be replaced, and it's actually pretty easy to see because I've highlighted it in blue. So something on the molecule is going to swap places with something else. Now I've decided to use some bromine in this particular substitution reaction because bromine is a very reactive molecule. It's also got a nice brownish reddish color, and that means you can tell when the reaction is happening. Now when you do these types of reactions, you'll see that these reactions don't happen without UV light. UV light is needed for halogens like chlorine, bromine, iodine, any of those halogens. Now when you're doing substitution reaction with halogens, you need UV light to be able to activate them. Now you do need to know this, and it is something that's unique to this type of reaction. So what's going to trade places? Well, I've got a hydrogen over here which doesn't come off very easily, and that's why we need the UV light, and one of these bromine atoms. So what I'm going to do is I'm going to swap places. I'm going to switch places between a bromine atom, so we're actually going to sort of trade them out. So this hydrogen is going to take the place of the bromine, and the bromine is going to swap in its place. These are probably the simplest types of organic reactions that there are. One thing swaps out for another. Now over here it doesn't actually matter which hydrogen swaps out because they're all actually the same hydrogen, and I want you to see if you can draw the product. And then we've got it. I've got HBr as a product. Let's just see what swap places. I had a bromine going into the place of the hydrogen, and the hydrogen going in place of the bromine. So you can see the blue hydrogen and the red bromine have now joined, and the bromine is now sitting on our organic molecule, and we've got one bromoethane. Very, very simple. We started out with a saturated product, and we've got a saturated, we had a saturated reactant. So there we go, that is saturated, meaning that there are only single bonds between the carbon atoms, and of course we've got a saturated product as well. You can see that this is very, very simple. Saturated to saturated is usually a sign that we've done a substitution reaction. Very, very simple. All that's got to happen is they've got to swap places. Now when you want to swap out a hydrogen with a halogen, you just need to remember that that needs a little bit of energy from some UV light. Now substitution reactions happen at relatively low temperatures, but they are very, very slow. It's very difficult to break a lot of these bonds, and these reactions happen really, really, really slowly. So substitution reactions very often can be distinguished from other types of reactions because they happen so slowly. Back in my research I used to do these things overnight in 12, 24 hours for these substitution reactions to actually happen. Very, very tough to get them to go. Okay, so we've got another set of reactants that we've had before actually. These types of reactants, I had a saturated reactant with NaOH, and you might be asking, why are you not doing an elimination? And here's the key, guys. Cool temperatures. Cool temperature is how do you make sure that a substitution happens and not an elimination. Elimination reactions tend to happen at higher temperatures. Now these sets of reactions could actually eliminate, and you could get ethene and a whole bunch of other reactions happening. But let's do the substitution because I've got cool temperatures, and also the sodium hydroxide should be dilute for this to happen. So let's take a look at what happens, and you might be asking yourself, I've got sodium hydroxide here, which is made up of two parts. I've got sodium there and I've got OH over there. They're two very different parts. Now I want you to think which parts are likely to swap. Now the way that I predict which parts are going to swap are the parts which are going to be roughly the same charge. OH is a negative charge, and so is bromine. So these are going to be the things which are likely to swap places. Very often you're not going to get sodium swapping places with bromine because sodium is usually positive and bromine negative. Usually you get the same thing swapping with the same thing. So a negative ion swapping with another negative ion, because bromine likes to be negative as well. So I want you to try to draw the product. I want you to try and predict it for yourself and see if you can do the product of this particular substitution reaction. I'm going to do it as well. I want you to pause the video and try it for yourself. Okay, so there we've got it. The substitution of 1-bromoethane using some sodium hydroxide. Let's just point them out. So there's my 1-bromoethane over there, and my sodium hydroxide, which was dilute to make sure that we are doing substitution. It's fairly simple. The OH is going to go in and replace the bromine, so bromine is going to be left up with the sodium bromide over there. And if you actually do these reactions in certain conditions, sometimes you actually see the sodium bromide coming out as a salt. It's inorganic, it floats, down to the bottom, and you actually get this really nice crystalline salt down at the bottom. Now the other product you should recognize, it seems to pop up quite often, is ethanol, so that's drinking alcohol. Although I don't recommend drinking this because it would probably have 1-bromoethane, and that's very likely to give you cancer at some point in your life. So guys, no drinking the products. Okay, so we've got these products very, very easy. Substitution just means a straight swap. We don't need to remember to make or break double bonds. We have a saturated reactant and a saturated product. Now here's the other thing that gives away a substitution reaction. You have the same number of reactants as products, and also both of them tend to be the same level of saturation. So saturated becomes saturated. Very, very easy. Let's do another one. Okay, so substitution can happen both ways, and substitution can happen, you can kick out a bromine with a hydroxide and can go the other way. If I use HBr, hydrobromic acid, can get a Br to swap out that OH. It tends to only happen with tertiary alcohols. That means alcohols with 3 carbons attached to the same carbon as the hydroxyl. But let's see what happens when we sort of swap this out. So let's just see which ones are going to swap and what's going to happen. So the bromine is going to go in there. So bromine's going to go in there, and what's going to happen is the OH is going to kick out there, and they're going to swap places. Very, very simple. I want you to see if you can name all these compounds as we go, because this is really good practice. And, it's very, very important. This is going to be done in gentle conditions, and let's see what we get out as a product. Okay, so I'm going to give you a moment or two to pause the video, try to draw the product for yourself, and we're going to go on with that. So what I've got here is the organic product, and a lot of people make a really serious mistake. They only draw the organic product and they forget to draw the inorganic product, which in this case, if you've done this right, the green part and the red part should go together to give me an H bonded to an OH. And if you've been watching anything that I've been doing here, that means that we've got water as a product. And there we go, 2 reactants, 2 products, straightforward substitution. Now there's one last type of substitution which doesn't usually get called a substitution because it's got a name all of its own, and you might recognize this. Esterification. Esterification is actually a substitution reaction. A lot of people don't see the pattern, but if you start taking a careful look on what's going to swap places, it's pretty important. Now the oxygens are going to swap places. That means that OH and H are going to get together. So let's draw that in. Let's see what sort of product we can get if we've got H and OH. And, I'm pretty sure you can figure this one out. Most of you have already figured out that this must be water. And water has got that HOH that we're looking for. So there we go, HOH, and that's my inorganic product. And let's take a look at the organic product that comes out here. What gets left behind once I take away that HOH? Well, the red and the black parts still have to combine. So when we've got these red and the black parts combining, life gets a little bit simpler when you start drawing it in a certain order. So I'm going to do exactly that. So there we go. We've got 1, 2, 3. And that's all joined to an oxygen in the middle. And I hope that you're starting to see and starting to name esters just as practice. Okay, so that's propyl. What is it joined onto? Well, there's something which came from the ethanoic acid over there. And the black part of this picture over there is joined on over there. Fantastic. So we've got propyl ethanoate. So just remember that making of esters is actually a type of substitution reaction. We had saturated before, we've got saturated afterwards. Please don't be put off by this double bonded oxygen. That doesn't mean that the carbon is not saturated. It's only double bonds and triple bonds between carbon atoms that make them saturated or unsaturated. So here again, esterification needs a catalyst of H2SO4. The reason for that is because H2SO4 is really good at getting rid of water or letting it get onto things. So it sort of helps carry things in and out of reaction, especially water. The H2SO4 is a catalyst, and this particular substitution reaction we need to drive a little bit faster. So this one we usually do at reflux. Now reflux is fairly high temperature, so you might be quite surprised at that, because all of the other substitutions take place at very cool temperatures, dilute. Now, the reason that we use reflux on this is we are actually trying to get this reaction to happen a little bit faster. And also because there's no significant risk of elimination unless the H2SO4 is very concentrated. Because you can actually do, for anyone that's really sort of into advanced chemistry, you can actually do elimination of water on the alcohol itself. You can actually destroy your alcohol. And that does sometimes happen. You will actually find a little bit of propene being made during this reaction, but usually you need much more concentrated sulfuric acid, H2SO4, and much more vigorous conditions. Guys, that's it for substitution. Please join again, and please remember to subscribe anytime I make a new video. Basically, these are free extra lessons, and we're going to be using them to teach in 2015. So if it's already 2015 while you're watching this, consider this revision.